Okay, what's my inside function? Right here, it's the first thing I do to x. And then my outside function is to take the cube root. If we take that cube root and rewrite it as a power, this looks a lot like the last example. Okay. So I don't have to decompose this. I can think in place here. Right. My inside function is what I first do to x, followed by my outside function, which is to take the cube root. So to evaluate this, I would have to take my number x and figure out this thing in the middle first, and then I do the cube root. To do the chain rule, you go the opposite direction. So I'm going to start with the cube root first, and then I'll worry about what's on the inside last. So to differentiate the cube root of something, I bring the exponent down and reduce it by 1. So we're taking the derivative of the outside function evaluated at the inside. And then we have to multiply by the derivative of the inside function. These get easier with practice. Maybe stop the video here and go look at a couple of the book problems, some of the low numbered ones, and you'll see some examples just like this that you can work. Right, how about this one? This one looks more complicated. Right. If I just had one of these, like this first part, I'd see, okay, that's a chain rule problem like our very first example. But now I have this piece multiplied by this piece. I really have two things going on here. If I want to take the derivative, I have a product of two functions, so I'm going to need to use the product rule. All right, and then when I go to differentiate each piece in the product rule, I'm going to need a chain rule. We will also see that there's some special simplification we can do here after we've taken the derivative, and this kind of simplification is a pattern that we'll repeat many times. So our product rule says I'm going to leave the first one of these alone, multiply by the derivative of the second, and then vice versa. So I'm going to leave this first term alone. I do nothing to it. I'm going to multiply by the derivative of the second term. All right, this is where my first chain rule comes in. So the derivative of something to the 6th power is 6 times that something to the 5th power. What is that something? X squared plus 2 times the derivative of the inside, 2x. So here's a chain rule. Plus, this plus here comes from the product rule. Now I have to differentiate the first term, so using a chain rule again. To differentiate a cube, I bring the exponent to the front, reduce the exponent by 1, leave the inside alone, multiply by the derivative of the inside. And now, so here's our chain rule. So we're differentiating the first, and we're going to leave the second part alone. Now notice here we have a lot of common terms. Right. On both sides of this plus sign here in the middle from the product rule, okay, I have some x squared plus 1s. Okay. Here I have 3 of them, and here I have 2 of them. So I can factor some of those out. Similarly, I have some x squared plus 2. There's 5 of them here, and there's 6 of them here. So between these two, I can factor out 5 of those. For the x squared plus 1s, I've got 3 here and 2 of those, so I can factor out 2. Right. And then accidentally here I have a couple other things I can factor out. There's a 2x here and a 2x on both sides. And there's a common power of 3 here as well. So what do I factor out? How much do I factor out? Right. I have 3 powers of x squared plus 1 here and 2 powers of x squared plus 1 here. I'm going to take out 2 of them. I take out the smaller power. Similarly, I have 5 of these and 6 of these. I take out the smaller power. I have a 2x in both places. I'm going to factor it out. There's a 3 here. This is 3 times 2. There's a 3 here, so I'm going to take that out. And then some big brackets. Now we write what's left. I took out 2 of these, so there's 1 left. We took out 3, so there's 6. There's still a 2 left. Took out 5x squared plus 2, so that's done. We took out the 2x, that's done. This plus, this is our original plus that came from the product rule. Took out the 3. Took out 2x squared plus 1, so this is out. We took out the 2x. We took out 5x squared plus 2, so now we still have 1 remaining. All right. Anytime I do a product rule combined with the chain rule, or a quotient rule combined with the chain rule, I will be able to factor out some common terms. Okay. Whatever I did the chain rule on, that's going to give me a common term I can factor out. There's a little more cleanup to do here. Let's see, we can 6x, x squared plus 1, x squared plus 2, 2x squared plus x squared is 3x squared, plus 2 is 4. Not much more we can do there. All right, let's see a similar problem but involving the quotient rule. Okay. I've got a quotient of 2 things here, so I need a quotient rule. And when I go to do the derivative of the numerator and the derivative of the denominator, I need chain rules. So let's jump in. Okay. First thing we're going to deal with is quotient. Right. We do the rules in the opposite of the order that we would use to evaluate this. Suppose we had a number x, like 5. Right? We'd take the 5 and plug it in here, and then we'd cube that number. Take the 5 and plug it in here, and then take that number to the 5th power. And the very last thing we would do is divide those 2 numbers. The very last thing we do tells us what the very first thing we have to do is when we differentiate. Right? Since the last thing we would do is divide, the very first thing we have to do to get a derivative is deal with that division or do the quotient. So we're going to do the quotient rule first. So low times d high. This is the chain rule. If I want to differentiate something cubed, I leave what's on the inside alone, bring the exponent to the front, reduce it by 1, and then multiply it by the derivative of the inside. All right, so there's a chain rule piece. Low d high minus high d low. All right, again the chain rule. 5 to the 4th power, leaving what's on the inside alone, multiplied by the derivative of the inside, all divided by low squared. If I square something to the 5th power, it's now to the 10th power. All right, just like when we did the product rule combined with the chain rule, when we do the quotient rule combined with the chain rule, there are going to be some things to factor out. Whatever we use the chain rule on, in this case both the numerator and the denominator, we're going to be able to factor out some of those terms. So here I should be able to factor out some 2x plus 1s and some 3x plus 4s. And again, I'm going to look at the numerator here, and I'm going to factor out, let's see, 3x plus 4. I've got 5 of them here and 4 of them there. I'm going to take out 4. I'm going to take out the lower exponent of the 2. And that generally works. I can factor out the lower exponent of the 2. 2x plus 1, 2x plus 1. Got 2 of those I can take out. I have a 3 in both places, so let's take that out. Now we use the brackets and we write down everything that's left on either side of this minus sign, which comes from the quotient rule. Took out 4 of these, so there's 1 remaining. We took out the 3, it's here. I don't need that. I took out 2 of these, so I don't need any more. I did not take out this 2, so it remains. Likewise, I took out 2x plus 1, so 1 remains. We didn't take out the 5, so it stays. We took out all these 3x plus 4's because we have 4 of them out front. So that we're done with that term, and we took out the 3. And this is, of course, over 3x plus 4 to the 10th. Right. One more cleanup step, and we're pretty much there. We're going to clean up what's in the brackets here. While I'm doing that, you may notice here I've got some 3x plus 4's upstairs and some downstairs. I can cancel off all those. If I have 4 of them up and 10 down, I can cancel off 4 and just be left with 6 in the denominator. Let's see, I've got 6x minus 10x is negative 4x. 8 minus 5 is plus 3. All right. Why do we have to do all that kind of simplification? It's a good question. Very often we need to know where a derivative is going to be 0 or where it's undefined. And when I look at it up here, I can maybe guess some of the zeros, okay, but I can't tell you that this derivative is going to be 0 if I put in x equals, what would it be, minus 3/4. Right? That's not really apparent here, or plus 3/4 rather. All right? I only get to see that after I've simplified, and I see that I can make the numerator 0 by making this term 0. So lots more on that later, but get used to that pattern of simplification. We're going to need it very often. Just think, if I had to set the derivative equal to 0, how would I solve? I couldn't do it from here. I could get some of the answers, but I couldn't find them all. But I can easily find the answers here once I have it in this kind of factored form. All right, same kind of plan here, but I want to see one here where we've got a fractional exponent on one of the terms. The simplification part works a little differently. Let's write this in calc-friendly form using powers. And jump right in. We're going to have a quotient rule, and then we're going to have a chain rule on one piece here. Ugh, you didn't see any of that. All right. Here's a similar looking problem. Right. It looks a little different because of the radical, and I want to do one of these where we have a fractional exponent involved, so we can see how that changes things. It only changes a little. Right. So we're going to take this square root here and write it in the more calc-friendly form as 2s plus 1 to the 1/2, and jump right in. We've got a quotient, so we're going to need a quotient rule. And at least on the denominator here, I'm going to need a chain rule. So low d high, which is just 2s, minus high d low. I have something to the 1/2 power, so I take that something, bring the exponent to the front, reduce the exponent by 1, leave what's on the inside of the alone, and multiply by the derivative of the inside. All over low squared. And now comes the cleanup. There's some clear, easy things we can do here. I can, the 1/2 and the 2, of course, cancel each other. Okay. I have an s on either side of the minus sign I can factor out. I also have some 2s plus 1s. All right. How many do I factor out, though, when I've got this fractional exponent? It's not quite as clear. What we're always going to do is factor out the smaller power of the 2. So we want to factor out minus 1/2 power. It's a little harder, take some practice with fractional exponents, but the idea is the same. We're going to factor out the smaller power of the 2. We're going to take out an s, and we're going to take out 2s plus 1 to the minus 1/2. Well, what's left behind? So here's our minus sign from the quotient rule. We took out the s here. We didn't take out the 2, so it's still there. And we took out some 2s plus 1s, but we didn't take out 2s plus 1 to the 1/2 power, so I'm still going to have some left here. How many? Well, what you need to think about is if I multiply these two terms back together, right, I'm supposed to get 2s plus 1 to the 1/2. If I multiply these things together, I'm going to add the exponents, and I need that result to come out to be 1/2. So minus 1/2 plus what gives me 1/2? Well, that would be 1. So I'm going to use an exponent of 1 here. Some people like to say, well, if I take out minus 1/2 of these and I have 1/2 standing there, then I get 1 left over. Right. On the other side of our minus sign, I took out 1s, so there's still 1 remaining, and we took out all of these 2s plus 1s. Downstairs, we've got 2s plus 1 to the 1/2 squared, or just 2s plus 1. Let's see where this goes. I'm going to take this guy, since it's a negative exponent, bring it down to the denominator. So I have s times 4s plus 2 minus s, 2s plus 1 to the 1/2, that came from the numerator, times 2s plus 1. Three s plus 2. Combining these two, I add the exponents, I get 2s plus 1 to the 3/2 power. Now that we have it in this fully simplified form, it's easy to see, or easier at least, to see where the derivative is equal to 0. That's going to occur if s is 0, or if this term is 0, at minus 2/3, and where the derivative is undefined, of course, at s equals minus 1/2. Practice that simplification. You're going to need it. Factor out the smaller of the two powers. Here's an example where we have to do the chain rule more than once in succession. This is really where the chain rule gets its name, because when we have a composition of functions that's a function composed with a function composed with a function multiple times, the derivatives are going to be differentiate once, again, again. It's a whole chain of derivatives. I'm going to write this in calc-friendly form. And let's jump right in. Right. The derivative of something to a power is that something. Leave it alone. Leave the inside alone. Okay. So I bring the exponent to the front, reduce it by 1, derivative something to a power, and the something alone, multiply by the derivative of the inside. All right. How do I differentiate this guy on the inside here? Well, x squared gives me a 2x plus, just take the 5 out of your way, it's along for the ride, derivative of e to the 7x. Right? Well, the derivative of e to the something is e to that something. Right? Now I have to multiply by the derivative of the inside here. So the derivative of 7x is 7. Right? So there were two chain rules involved. This chain rule times the derivative of the inside, and then this chain rule. I had to multiply by the derivative of the inside of the exponential function. Right? So as an aside here, the derivative of e to some stuff is e to that stuff times the derivative of that stuff. Right? It's kind of a special case of our chain rule, but one we'll get used to. Here's another example where the composition of functions is more transparent. I take my number x and apply the tangent function. To that result, I apply the cosine function. To that result, I apply the sine function. So to undo this, when I take the derivative, I'm going to have to apply the chain rule more than once. I start with the outermost function. The derivative of sine of some stuff is cosine of that stuff. Now I have to multiply by the derivative of the inside. The derivative of cosine of some stuff is minus sine of that stuff. Right. Then I have to multiply by the derivative of the inside. The derivative tangent of something is secant squared of x. Right. I only get to stop multiplying by the derivative of the inside when I get down to just my variable all by itself. So when I take the derivative tangent of x, I get secant squared of x. I feel like it's times the derivative of x, but that's just 1, so nothing to do there. Right. So we have two chain rules, one here and one here. We already know that the derivative of e to the x is e to the x, but how do we differentiate an exponential and another base? And this is going to be one of those rules that you just need to memorize. Here's the trick. All right. Derivative of 2 to the x, or y equals 2 to the x. I can take 2 to the x and I can rewrite this 2 here as e to the natural log of 2 and raise that to the x power. E and natural log just of course cancel each other out. That seemed like a stupid thing to do. Right? But e to a power raised to another power, I can multiply the exponents. So this is the same thing as saying e to the x times the natural log of 2. Right? And now I see I can do a chain rule. To take the derivative of e to some stuff, I take e to that stuff, and I multiply by the derivative of the inside. The derivative of a number times x is just that number. The number in this case is natural log 2. Right. So what did we do? Right. We rewrote the 2 to the x using base e. Base e we know how to differentiate. And when we did that, we had a natural log 2 that somehow pops out there. This part, right, this is just 2 to the x rewritten. So y prime is equal to 2 to the x times the natural log of 2. Derivative of a to the x is always going to be the natural log of the base times a to the x. In the case of the base e, we know that the natural log of e is 1, so we never see that term. Right. Let's use this here. Right. I have 2 raised to the sine x power. So the derivative of an exponential function is an exponential function. So the derivative of 2 to the stuff is the natural log of 2 times 2 to the stuff times the derivative of the inside. This is a little confusing. Right? Derivative of 2 to the stuff is 2 to the stuff, and then you have this little natural log 2 that pops out. If we have the derivative of 5 to the x squared would be 5 to the x squared. The derivative of an exponential is always an exponential. I have a little adjustment here because the base is not e, so I'm going to have to multiply that by the natural log of 5 times the derivative of the inside, 2x. It takes practice. Be sure to try that problem in your homework. All right, that's all for now.